The Sun, a G-type main-sequence star, is the central and most massive body of our solar system, accounting for about 99.86% of its total mass. Located approximately 93 million miles or 150 million kilometers from Earth, it provides the energy necessary for life to exist on our planet. The Sun's diameter is about 1.39 million kilometers or 864,000 miles, making it 109 times wider than Earth, and its mass is roughly 330,000 times that of our planet. Composed primarily of hydrogen, about 74%, and helium, about 24%, with traces of heavier elements like oxygen, carbon, neon, and iron, the Sun is a massive ball of hot, ionized plasma held together by gravity. Its energy is generated in its core through nuclear fusion, where hydrogen nuclei combine to form helium, releasing enormous amounts of energy in the form of light and heat. The core, which extends out to about 25% of the Sun's radius, reaches temperatures of around 15 million degrees Celsius and pressures so intense that fusion reactions can occur. Surrounding the core is the radiative zone, where energy slowly migrates outward in the form of electromagnetic radiation. This region is so dense that it can take thousands or even millions of years for photons to travel through it. Beyond the radiative zone lies the convective zone, where hot plasma rises and cooler plasma sinks in a process called convection, which helps transport energy to the Sun's surface. The surface of the Sun, known as the photosphere, is the layer we can observe directly and emits the light that reaches Earth. It has a temperature of about 5,500 degrees Celsius and appears granulated due to the convection currents beneath it. Above the photosphere lies the Sun's atmosphere, which consists of the chromosphere and the corona. The chromosphere, visible during a solar eclipse as a reddish glow, is a thin layer where temperatures range from about 6,000 to 20,000 degrees. Beyond this, the corona extends millions of kilometers into space and can reach temperatures exceeding 1 million degrees Celsius, a phenomenon that remains a subject of scientific investigation. The Sun's magnetic field, which is generated by the movement of charged particles within its interior, plays a crucial role in its activity and behavior. This magnetic activity gives rise to phenomena such as sunspots, solar flares, and coronal mass ejections. Sunspots, which appear as dark patches on the photosphere, are cooler regions caused by intense magnetic activity. Solar flares are sudden eruptions of energy caused by the reconfiguration of magnetic field lines, and CMEs are massive bursts of solar wind and magnetic fields released into space. These events can have significant effects on Earth, including disrupting satellite communications, causing power grid failures, and producing beautiful auroras near the poles. The Sun undergoes an 11-year solar cycle during which its magnetic activity waxes and wanes. At solar maximum, sunspots and solar storms are more frequent, while at solar minimum, the Sun's activity decreases. The solar wind, a continuous flow of charged particles emanating from the Sun, spreads throughout the solar system and interacts with planetary magnetic fields and atmospheres. This wind creates the heliosphere, a vast bubble that extends well beyond the orbit of Pluto and acts as a protective shield against cosmic radiation. The Sun's energy output, known as solar irradiance, is remarkably consistent, though small variations can influence Earth's climate over long timescales. The Sun is approximately 4.6 billion years old and is currently in the middle of its life cycle. It is expected to remain in its stable hydrogen-burning phase, known as the main sequence, for another 5 billion years. Eventually, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets, including possibly Earth. After shedding its outer layers to form a planetary nebula, the Sun will collapse into a white dwarf, a dense, Earth-sized remnant that will gradually cool and fade over billions of years. Understanding the Sun is vital not only for comprehending the dynamics of our solar system but also for studying other stars and the potential for life elsewhere in the universe. Observations and data from solar observatories, such as NASA's Solar Dynamics Observatory and the Parker Solar Probe, continue to enhance our knowledge of the Sun's structure, activity, and influence on space weather. Despite its apparent constancy, the Sun is a dynamic and ever-changing star. Its light, which takes about 8 minutes and 20 seconds to reach Earth, sustains life by driving photosynthesis, regulating weather patterns, and influencing the planet's climate systems. The Sun's role as the primary energy source for Earth underscores its importance in shaping the conditions that make life possible. Throughout human history, the Sun has been a central figure in culture, religion, and science, revered as a deity in many ancient civilizations and studied extensively in modern times. With ongoing advancements in solar science, researchers aim to unravel the remaining mysteries of our star, such as the mechanisms behind the solar dynamo, the origins of its magnetic field, and the processes that heat the corona to such extreme temperatures. In conclusion, the Sun is much more than a bright object in the sky. It is a complex, dynamic, and life-sustaining star that continues to captivate and inspire scientists and laypeople alike. Its study not only helps us understand our place in the cosmos but also prepares us for future challenges, such as mitigating the impacts of space weather on our increasingly technology-dependent society. By continuing to explore and monitor the Sun, humanity gains valuable insights into the fundamental processes that govern stars and the universe at large. The Sun's influence extends far beyond its immediate surroundings, shaping the entire solar system and affecting interplanetary environments. One of the most significant effects of the Sun is its gravitational dominance, which holds all 8 planets, their moons, asteroids, comets, and other objects in orbit. This gravitational pull also governs the orbits of smaller celestial bodies, such as the Kuiper Belt and the distant Oort cloud, regions filled with icy objects and potential comets. The balance between the Sun's gravity and the angular momentum of these objects ensures the stability of the solar system over billions of years. Additionally, the Sun's position within the Milky Way galaxy plays a crucial role in our cosmic neighborhood. Located in the Orion Arm, about 26,000 light-years from the galactic center, the Sun orbits the Milky Way at an average speed of approximately 828,000 km per hour, completing one orbit every 225 to 250 million years. This journey through the galaxy exposes the solar system to varying cosmic environments, including regions of interstellar dust and gas, which can influence the heliosphere and potentially affect Earth. The Sun's magnetic field is a complex and dynamic structure, constantly evolving due to the movement of charged particles within its interior. This field extends outward into space, creating the interplanetary magnetic field, which interacts with the magnetic fields of planets and other celestial bodies. The Sun's magnetic activity is responsible for a wide range of space weather phenomena. For instance, solar flares and coronal mass ejections can produce bursts of radiation and high-energy particles that travel across the solar system. When these particles interact with Earth's magnetic field, they can cause geomagnetic storms, disrupt satellite operations, and create dazzling auroras. Scientists closely monitor the Sun's activity to predict these events and mitigate their potential impact on technology and infrastructure. Space weather forecasting has become increasingly important as humanity relies more on satellites for communication, navigation, and other critical services. The Sun's energy output, or solar luminosity, is a vital driver of Earth's climate and ecosystems. Over geological timescales, variations in solar output have contributed to natural climate cycles, such as ice ages and interglacial periods. While the Sun's energy is remarkably stable over short timescales, small fluctuations, known as solar irradiance variations, can influence climate patterns when combined with other factors like volcanic activity and greenhouse gas concentrations. Scientists use a combination of satellite observations and models to study how solar variability affects Earth and H039's atmosphere and climate. This research is essential for understanding the interplay between natural and human-induced climate change. In addition to its physical and scientific significance, the Sun has played a central role in human culture and history. Ancient civilizations, such as the Egyptians, Mayans, and Greeks, revered the sun as a deity and aligned their religious practices, calendars, and architectural designs with solar cycles. Structures like Stonehenge, the pyramids of Giza, and the Mayan pyramids at Chichén Itzá were designed to track the sun's movements and mark significant astronomical events such as solstices and equinoxes. The sun's predictable rise and fall shaped early agricultural practices, enabling societies to develop farming techniques and sustain civilizations. Modern science has demystified the sun's nature, yet it continues to inspire awe and wonder. Advances in solar observation technology have allowed scientists to study the sun in unprecedented detail. Instruments like the Solar and Heliospheric Observatory, the Parker Solar Probe, and the European Space Agency and HH-039's solar orbiter have provided critical insights into the sun's magnetic field, solar wind, and corona. The Parker Solar Probe, launched in 2018, has ventured closer to the sun than any previous spacecraft, flying through the corona to study its properties and uncover the mechanisms behind its extreme temperatures. These missions contribute to our understanding of stellar physics and improve our ability to predict and prepare for solar activity and HH-039's impacts on Earth. Looking toward the future, understanding the sun will remain a priority as humanity ventures further into space. The sun's energy and behavior will play a crucial role in sustaining life and powering technologies on other planets or in deep space habitats. By continuing to study our star, scientists not only unlock the mysteries of the sun but also gain broader insights into the behavior of stars throughout the universe. As the cornerstone of our solar system and the enabler of life on Earth, the sun remains an object of endless fascination and discovery, bridging the realms of science, history, and imagination.